one of the most successful and most widely used models in coarse graining. But even in this case, you will observe that there are differences from external. So the density may not match perfectly at room temperature, or if you match the density, you might not match the dielectric constant and so forth. So there's many challenges in this regard with regards to how to develop these parameters and how you capture every single parameter. So one of the things we recently looked at is looking at simple coarse-graining models for water. And we're basically not so much interested in looking at charges and screening effects and so forth. We're thinking we can probably put these externally into the system by using a dielectric field or using effective interactions. So there are two approaches in these class of models, basically replacing every water molecule with a single bead. So the first approach is based on a Lennard-Jones-based coarse-grained model. So instead of two molecules or several molecules, you just have two Lennard-Jones particles that represent a collection of molecules. And then you try to match the same kind of behavior as the bulk water. One thing we observed with this case is we're looking at this from applications in large-scale applications of capillary flow and so forth. And there's some issues where you have catastrophic freezing of the molecules. So all of a sudden your system will freeze, and then you can't really run the simulation anymore. And then there's other methods such as distributed particle dynamics, which have very soft potentials, which get rid of these issues, but then you have an issue of atomic overlap. So if you are looking at the polymer solution, you might have chains that are overlapping with itself, with each other, which physically makes it hard to make interpretations in many cases. So what we looked at here is basically something in between these two cases, which is a Morse-based potential. And what we observe is that since the potential is softer, you don't have the freezing issue, which really has to do with rigid particles clustering in near surfaces. And the other thing is we got pretty good agreement with the density of water and the diffusion constant of water at room temperature. So we think that using the Morse potential for these applications might allow us to do larger scale calculations without having to calculate electrostatic interaction and so forth. So the whole idea is to have some parameters that we can change that represent surface roughness and hydrophobicity and these kind of things, and the discrete nature of molecules or molecular conditions without really going into too much chemical details. And, we're going to pursue this work in the near future. Hope that it works in terms of the cost graining. And I'm going to go back now to the case of the cyclic peptide with these nanotube structures. And for these, we're interested in modeling these at larger length scales. So the approach we're taking is calculate the binding energies in the axial direction. So this gives us a measure of the elastic modulus of the material. And then you can calculate the torsional properties of cyclic peptides from molecular dynamic simulations as well. And then feed these mechanical parameters into a coarse-grained model. So in this simplest case, what we want to do is really match the mechanical overall features and the structural features to a large extent. And the question is, of course, how do you do these torsion simulations? And one thing you can do is basically allow the molecule to rotate and then bind and rebind. And then by doing so, you can calculate the energy landscape as a function of rotation angle. And when you do that, you can observe that it's a very bumpy surface. The reason being, you have hydrogen bonds forming, and then as you shift the molecule a little bit, you get very strong repulsions because it's two electronegative atoms that are overlapping. And then once you go over that barrier, you again form a hydrogen bond, which is another energy dip. So it's sort of this bumpy surface kind of system that we sort of have to replicate in the coarse-grained simulation. So we thought a little bit about what would be the easiest way to do this, and this is sort of a preliminary idea that we're pursuing. Perhaps we could use certain charges that are alternating, which basically creates the same kind of electrostatic repulsions, and then basically gives the material this shear rigidity that the real nanotubes have. The one thing you can find with these simulations is that if you use typical Lennard-Jones type interactions and so forth, we get shear rigidity. In the case of actual nanotubes, electrostatic interactions really give the shear rigidity to the material. Because as you try to rotate it, you don't have the same alignment of charges that you have with hydrogen bonding. So with this kind of simplistic models, we think that we can at least get the shear rigidity and the elastic modulus correctly, and then that would help us predict the persistence length at longer length scales, and also the conjugation of the hydrogen bonds in the formation of the nano. Okay, so the output basically for the organic nanotube membranes is we need to understand the formation and failure mechanisms and look at multi-scale simulations in combinations with experiments to quantify transport rates, look at the role of mechanical stress, and understand how the assembly process works and chemical structure and mechanics are related for these nanotube systems. And hopefully this will lead to next generation gas separation membranes. Okay, so this is sort of the first part of what I wanted to discuss. In this case, what we did was we went one scale up, or talked about how to go one scale up in the length scales of simulation. Another question that often we need to deal with is how do you go one scale down, or how do you incorporate quantum level details into a regular molecular dynamic simulation. So this is the next part of the talk, where we do talk about reactive simulations. So basically this is where we stand. We were here and then we went up to mesoscale models, and then now we're going into reactive simulations where we want to capture some of the critical quantum mechanical effects that we typically can't do with molecular dynamics. So the main challenge here is chemical reactions. So in the case of molecular dynamics, you have a fixed number of bonds and fixed connectivities in the molecules to simplify the calculation. The question here is if you have these harmonic interactions, you really can't have transitions from one hybridization state, let's say, to another hybridization state. The reason is because you don't have any description of electronic events. What we do is instead we have these covalent bonds represented by harmonic springs. We change the stiffness of the springs and so forth when we have different kinds of bonds, but the transitions between these cases are not very easy to capture. So when we need to capture a bond breaking or covalent bond breaking as opposed to hydrogen bonds and so forth, we need what we call a reactive simulation approach. And the key features of reactive potentials, there's many flavors of this, is that you need to accurately describe specific transition energy during chemical reactions, and then use computationally efficient descriptions derived from quantum mechanical methods. So you want to do this in a limited time scale, but be able to capture this transition from one state to another fairly realistically. And other features, basically, this landscape has to be continuous. There's typically no atom typing necessary, so we don't have different kinds of carbon atoms or anything like this. We just have an overall system with elements that have certain features that can vary. And then it has to be computationally efficient so that you can treat large systems, otherwise it's limited in its impact. And all of these parameters should have physical meaning to a large extent. And there's many different approaches to how you do this for, let's say, protein materials. And one approach is QMMD, QMMM kind of approaches, where you do part of the system is treated quantum mechanically, other parts are treated with molecular dynamics, and then you have to activate and deactivate these regions. This is one of the most commonly used approaches, but then you need to know when you need to activate the quantum mechanical treatment versus non-quantum treatment, and this is very challenging for certain reactions. And then there's some semi-empirical methods such as tight binding and so forth. And then the third is basically added abilities to simulate reactions with the classical force field method. So all of the simulations you've seen with carbon nanotube fracture or graphene fracture, these kind of things, typically they have these reactive kind of potentials. Covalent bonds breaking and changing the states. And there's many different flavors, thirst of Brenner, IVO, reactions, some that come to mind. the basis of these potentials is basically you have a bond order description. So what happens here is that you have a pair potential that depends on the atomic environment. So it's similar to the embedded atom method, but here applied more to the covalent bonds. And this is called the bond order idea. So the strength of the bond changes as you change the chemical environment. And this has to be a continuous transition. And then one of the earliest ideas was developed by Brenner, who basically applied this concept to the case of carbon. And this relates to the concept of hybridization. So if you have a ground state electronic configuration of carbon, this dictates the possible bonding scenarios, which can be quite diverse. The number of valence electrons relates to the number of bonds you can have. And carbon in particular has different hybridization, so it can be sp3, sp2, or sp, where you can have a triple bond or a double bond or a single bond. And the idea is basically define a numerical description of this changes in the bond order or the strength of the bonds, and make it smoothly so that you can have, as you stretch the bond, you can go from triple to double, or depending on the chemistry of the environment, other kind of transitions. And essentially, now compared with the classical potentials, where you have bond length and energy, which are directly related, you have bond length, bond order, and an energy constant. So all energy terms are dependent on this bond order constant. And then historically, this is not a very new idea, but it has been applied to different kinds of systems, and there are still many challenges as to how we do this. So the topic I have here is more related to the reactive potential, which is a particular flavor of these simulations. So this is the original paper of the reactive force field. This was developed by Adrian Doing and Bill Goddard at Keten, and now it has been applied to many different kinds of chemical systems. And then it's again the same concept. You basically break it down into different energy terms, and then you can have multi-body or two-body, three-body interactions. And then all connectivity type expressions are in terms of, in this case, bond order. So chemical environment plays a major role. And the key thing to consider here is that the energy between two particles doesn't only depend on bond distance, it depends on the bond order. So chemical environment plays a role. And we have many different bond order functions in this case, where you can have a pi bond or sigma bond, double pi bond, and these can basically vary smoothly to express these transitions. One of the key differences with these reactive force fields and regular force fields is that when you have calculation of charges, in the classical force fields such as charm, the charges are fixed, so you don't have a charge separation of changes of these electrostatic interactions. In certain scenarios, you read, especially if you look at reactions, this equilibration of charges is a very important difference. I mean, it can make a difference in your interaction energies and other calculations. So there's a method called QEQ method that is used in reactive field to calculate charges at every time step. And of course, this is why it's a lot more time-consuming to do reactive simulation. You basically have to know charges at every step and recalculate them using sophisticated methods. So, specific case of reactive FF, there's many different flavors of it now, and you can essentially apply it to a lot of the different atomic structures, interface metals, ceramics, organic chemistry, other biological materials, with the rising application area as well. Okay, so our application is mostly related to protein materials. So, and I think it's a very exciting application, but also a very challenging one. So the idea here is we talked a little bit about the 20 different amino acids, and among all of these amino acids, cysteine is the only one that is capable of cross-linking via disulfide bonds. So these are essentially covalent links that can bind two parts of a protein or two different proteins to each other very strongly. So it's different than hydrogen bonds. It's sort of a weak covalent bond. And it basically happens through what we call an oxidation-reduction reaction. So basically, if you have a proton or a thiol group and an oxidizing agent, you can basically release the hydrogen and then form the sulfur-sulfur bond. And then you can also go the other way and have a reducing amide. Why is this important? Well, this is very important both from a mechanical perspective and structural perspective in biology. If you look at a lot of materials like hair and wool, swelling, curliness, extensibility of these materials are really governed by these crossings. So chemical crossings play a major role in these materials. And it also has been used for years in vulcanized rubber. So rubber also has these sulfur bonds that are used for cross-linking, and that improves the mechanical and thermal properties of tires. So all the tires we use today have these kind of cross-links. And then it also plays a role in different kinds of keratin that we find in biological systems. So you might have nails or hard keratin in beak and other types of hard materials. It's very interesting because these are different from a lot of the strategies that we observe in biology for creating hard materials. Typically what we observe is biomineralization. So in the case of bone or shells or other kinds of systems, you have minerals incorporated into the protein matrix. In the case of these materials, they are still very stiff, but this is achieved by heavy cross-linking of the protein material. So they don't involve necessarily mineral structure. So this is why it might be of quite a bit of interest from the mechanics perspective. So how strong are these disulfide bonds? They are much weaker than the triple, double bonds, etc. that I mentioned earlier. But they are much stronger than what we consider as the strength of hydrogen bonds. So they have sort of an in-between scenario for achieving strong crosslinks. What are the other applications of these? Well, these disulfide bonds are extremely important for protein folding. So in the extracellular matrix, we have more of an oxidizing environment, whereas within the cell, we have more of a reducing environment. So this is utilized in biology to control when proteins are going to fold and form certain kinds of structures. And in the case of diseases, this balance of oxidation and reduction can be actually manipulated in a converse way such that you might have formation of proteins prematurely that causes a misfolding and aggregation. And then the body has a lot of mechanisms to try to reverse this process. So you might have hypertension, which increases mechanical stress in the vascular system, which inhibits certain cascades of chemical enzymes and triggers an oxidative stress, and then you can have a chemical response again, which tries to diminish that. And then the body tries to find that balance of chemical and mechanical stresses that it's constantly subject to. In the case of, from a materials perspective, it really governs the soft to rigid transition in protein materials. So you might have something that behaves like a noodle within the cell or within the protein synthesis process, but once these polypeptide chains exit the cell and they get oxidized, all of a sudden they form these very orderly fibrous structures, which are basically, their reference shape is defined by these crosslinks. So this is a major application. And in the case of other kinds of applications, such as misfolding, then these crosslinks form in the wrong way, and then you have fiber formation. So from a material design perspective, we're interested in this because we can probably make materials that are multifunctional. So they are responsive to their chemical environment. So by changing it from an oxidizing environment to a reducing environment, you can have reversible connectivities and change the shape of the material. And this is key for hierarchical structures and also drug delivery vehicles. So for instance, if you want to use this redox gradient within the cell and outside the cell, you can have a particle that is stable outside the cell that goes into the cell via endocytosis, and then this redox change can basically break the crosslinks and then deliver the drug. So there's already applications of this redox potential difference. And then you can also use it for all kinds of different materials applications. These include wheat, gluten proteins, and other kinds of proteins that we find in nature, such as the turtle shell, scutes, and so forth. So in silico, this is, as I mentioned, hard to do because we have these harmonic descriptions and we can't really break the bonds. So for this reason, we use reactive force fields, and we try to basically get a deeper understanding of how these bonds break as a function of reactivity. So these are the key functions of reactive F that makes it that makes us able to capture some of the aspects that we're interested in: changes in charges, changes in bond order, and computational efficiency that we can't easily do with other methods. So we started at looking at the simplest system we can have, which is basically a single disulfide bond where you can apply mechanical strain to it, and then also try to reduce it using simple reducing agents, even as molecular hydrogen in this case. And then what you observe is these are basically model systems where you try to mimic a certain kind of reducing potential. So in one case, we might have a hydrogen molecule attacking this sulfur-sulfur bond. In the other case, as a false test, you can have an oxygen molecule trying to attack this sulfur bond. And of course, these are not very likely reactions in real life, but we're interested in what would be the likelihood of this reaction when you have a certain bias potential and compare the different chemistries. So these are sort of model systems that we look at to understand the stability of the bond in model reducing environments. And then what we observe in the case of hydrogen is that we can have this full reaction occur, so these SH groups are formed. In the case of oxygen, regardless of how much you try to bias the molecule, it's not very likely that this bond is going to break. Instead, the other bond, which is a carbon-sulfur bond, is more likely to break. And this idea is utilized in biology to change these crosslinks very easily. So you apply a little bit of mechanical strain, and then you apply a chemical signal that tells the sulfur bond that in a reducing environment is supposed to break. And then you can rearrange the molecule and refold or change the shape. And this is utilized in biology. In the cases where you don't want the bond to break, then there are other strategies. So I'm going to talk about that next. But the key idea here is that by changing the chemical environment, you can change the force you need to be able to break these covalent bonds. And you can also think of the energy required to break the bond as a function of chemical environment. So what happens if you don't want the bond to break? In that case, what we observe in biology is that the disulfide bond is buried into the core of the protein. So it's not accessible to solvent, or it's not accessible to the kind of agents that can break this chemical bond. And this is very, very common in a lot of extracellular matrix proteins. So the bonds are created such that they cannot be broken. And then you can do simple simulations where we want to understand how, for instance, how accessibility of the molecule plays a role in the chemical strength of the porosity. So in the case where you have the reducing agent far away from the molecule, you can't really have the breaking of the bond, whereas in the case it's very close to the molecule, then the breaking of the bond becomes much more favorable. And then we looked at some of the reaction mechanisms with dithiazolidine, which is one of the most commonly used reducing agents. And qualitatively, we get some good agreement with the experiments in the sense that when you have an attacking bond, you have this partial state where you have bonding of the sulfur into the original bond, and the original bond breaks, and you have what we call disulfide shuffling. So bonds are shuffling. And then you can also characterize the distribution of how much strain you need to apply, and how close the other sulfur molecule has to be in order for these reactions to occur. And this is sort of a simulation of how these reactions typically occur in these reactive simulations. So here, these lines are basically showing bonds that can form and break. So you're also applying a mechanical strain in this case to speed up the process of breaking. So overall, I mean, this is sort of the start of something very difficult to do computationally, and we're trying to understand how these sulfur bonds break, and then feed this into larger scale descriptions of fibrous proteins. And this is sort of interesting in the sense that we haven't really looked at this from a continuum perspective. This chemical ingress is a problem that is very hard to model with many approaches we have so far. We observe that the exact fraction mechanism is very much dependent on the localized features such as accessibility of the specific crosslink, as well as chemical environment, availability of reducing agents, and so forth. And we're hoping that we can use the reactive formulations to really understand how the chemical bonds can break in different environments. And then the outlook is basically compare these with quantum calculations and experiments, and then investigate the dynamics of large polymeric and protein systems where you can have multiple crossings and shuffling between these different crossings to create some sort of a multifunctional system. That's basically all I had. I went through 3 or 4 different topics very quickly, but if you have any questions, I will be happy to answer them. But I think this sort of gives an overview of pretty much all of the methods that are accessible to us, and all of the challenges there are, and all of the interesting applications that we're looking into. Thank you.
How expensive is React's potential in terms of computing?
It's fairly expensive. I mean, I think I had some numbers, but typically it's at least 10 times so, but sometimes more. As you go into larger and larger systems, the charge calculations become very expensive.
Is this order and how's the scaling here?
Scaling is good because we use the same programs that we have, like lamps, etc., that are fairly parallel. So we didn't have too many issues with scaling, but we didn't look at very large systems either. So if you have 1,000 atoms, it's not scalable anyways. But in other systems, I think scaling has worked well for carbon nanostructures or graphene, these kind of applications. I don't think there was too much scaling issues, but there's a lot of issues with how to capture reactions. I think that's a really hard problem to solve at this dynamic environment, coupled with mechanical stress.
There's some kind of technique like submodeling that is done in finite element simulations where when you analyze large structures to reduce the computation on power to be able to explain the phenomena.
Yeah, so I mean...
is there similar technique available in
yeah, I mean, I've seen studies where you couple it with reaction diffusion time equations. So you can basically try to model what kind of what's happening with what kind of chemical reactions can occur, what are the energy barriers, etc., and write a differential equation that describes that phenomenon, and that we can try to capture it at a continuous scale. The issue with the redox problem is that it's a very localized problem, so it's very much dependent on not so much the field, but the field effect of the actual localized feature of that heterogeneous structure. So one bond may be exposed and it might be more likely to react, whereas another one may not be exposed very easily and it might be much less prone to reactions. And the structural features we're looking at is at the angstrom scale. So with any finite element treatment, this is fairly difficult.
No, I'm not mentioning the finite element treatment, but to see a correspondence between in finite elements, when we want to analyze very large structures, aircraft structures and all, then they use submodeling technique. So that they can transfer these submodeling analysis to the next level and then be able to explain the complete phenomenon. So similarly, do we have such kind of philosophy in molecular dynamic simulation process so that we can analyze large systems?
Right, yeah. So that's what we want to do, basically feed this into an effective potential that is dependent on the local structure that is basically a coarse grain description. So it's basically fitting effective potentials and or probabilities of bond breaking into coarse descriptions. That's the equivalent of how much it can capture is dependent on how well you can do this kind of multi-scale. That's the idea. Doing the reactive simulation